Please welcome a software engineer at Croyd, an active young member of the upstream Ceph community. His talk, Faster Cephfs Mirroring, addresses a critical problem, a single thread limit and slow rescans after failover. He will present two innovative practical improvements. First, adaptive parallelism using a bounded frontier algorithm, and second, snapshot-aware recovery that drastically shrinks recovery time. Welcome from Koblenz, Mahamudur Rahaman Sajib. Please.
So, hello everyone. I'm Mahamudur, currently working as a software engineer for Croyd. I have very little experience with Ceph, more than 1 year. So in this 1 year, I try to look into the bit in the code base, and sometimes customer asks for some bug fixes or some issue. I try to look into there and try to find some problem and solution. That's overall my activity in this 1 year. So while regarding Cephfs-mirror, anybody used it before Cephfs-mirror here? Yeah, I think there is a good reason to not to use it, because it's very slow right now and not usable, not in a usable condition, I would say. So, we found some customer was having trouble with Cephfs-mirror because it's very slow and single-threaded, not single-threaded actually, but okay, we will talk about it, but it's very slow. So that's why I take a deeper look there and did some improvements while writing some code in Cephfs-mirror. So let's go. So how Cephfs-mirror works on high level. So you have two clusters. One is local source cluster and one is remote cluster. So you can register, it's a daemon, like other daemon as in Ceph. You can add directory, which directory you want to mirror, and then goal of the directory basically replicate the .snap directory from local to remote. So every time you take a snapshot, that snapshot will be synchronized to the remote cluster. So we have done one example like local snapshots. Let's say snap 1, you take snap 2, snap 3, snap 4. And idea is advance those, like the delta between, let's say, snap I and snap I plus 1, try to transfer those delta to the remote cluster. That's the most optimized way, instead of just completely synchronizing the whole snapshot. Okay, so just to give an overview, the delta application concept is not very complicated. Like you take snap 1, that is your remote base. Let's say your remote base is totally corrupted, it will handle it. So it will send that delta between snap 1 and base and transfer it to the remote cluster, and so on and so forth for other snapshots. So incrementally, whenever you incrementally take a snapshot, all the deltas will be transferred to the remote cluster. So some improvements were previous and current Cephfs-mirror. So we try to write a bit comparative problems and fixes. So it's a bit rigid. It has concurrency, but there's rigid concurrency. Like, for example, you registered a directories. You can register multiple directories. So each thread will be responsible to synchronize for each directory. So there can be problems like load imbalances. Like, for example, you have a larger directory and you have a smaller directory. So larger directory you expect to sync later than a smaller directory. So when your smaller directory finishes, that thread is just sleeping. So, we are not utilizing the cores and our bandwidth. And so what we did, kind of flexible concurrency. So we try to granularize the tasks, and using thread pools, we try to globally use how many threads you want to use for file mirroring. Let's say we have a mirroring pool for file mirroring, another mirroring pool for metadata IO. So the user can decide how many threads I will want to use for file mirroring, how many threads I want to use for directory scanning, and so on and so forth. So result is a bit load balancing between the threads and no idle cores. Let's go to the next page. So another optimization we try to do is failover and resume inefficiency. Like for example, failover is in Cephfs-mirror, failover is inevitable. So basically, whenever a failover happens, your remote cluster is corrupted. So the remote file system is, inconsistent. Corrupted is not a correct word. So in that case, when you restart again, at that time, you might need to rescan the whole remote. Current procedure is you rescan the whole remote, finding the delta, and transfer those delta to the remote cluster. But we try to think about this way. Let's say whenever we are trying to synchronize snapshot, we are trying to always try to find the delta between previous snapshot and current snapshot. So we can predict which part of your remote file system subtree is actually inconsistent. So instead of the user don't want to have a very good hardware in their remote cluster. So we try to reduce the calls to the remote cluster as less as possible. So basically, we try to evaluate which parts has the difference between the previous snapshot and current snapshot. We only traverse those delta regions in remote cluster. So that's why the failover and resume efficiency is there, because as I said, remote cluster is not, your backup cluster is not having good hardwares. So net effect is, previously it was underutilized CPU, bandwidth and higher tail latency, and longer recovery after interruptions. But currently we have properly utilized CPU and bandwidth and lower tail latency. Basically, even if there are some MDS limitations as well. So with that, we try to utilize between those. So just for the summary, let's say previously it was part directory thread, rigid concurrency. Now it's thread pools, tunable concurrency. Load tied to directory count size previously, because one thread will use one directory completely synchronizing. So now granular tasking spreads work evenly across threads. And also previously snapshot schedule mismatch was one problem, because you don't take snapshot for every directory at the same time. You take, let's say 1 hour later, another directory snapshot. So there is a chance that is we are not utilizing the concurrency. So here it's just globally. For example, if you are using 8 threads and currently 2 directories are on sync, then that 8 threads will synchronize those 2 directories. If, let's say, your snapshot schedule is allowing you for 1 directory, then those thread will completely focus on that 1 directory. And as I said, failover and delta remote. Previously, there was some problem with unpredictable memory, because you might need to take the whole file system level into a memory. There was some fixes now, but now we have predictable memory because we can limit the queue size. And now, previously it was hard to tune, and now simple knobs. How many scanner threads you want, how many file copy threads you want, queue capacities, and in-flight bytes. So on a high level, just to share concurrency approach. So there are 2 kind of thread pool. One is directory metadata pool, as I said, and one is file data pool. So why this work? Actually, granular tasks and balanced load, and also user configurable scaling. So you can adjust your scanner threads. Maybe, let's say, for example, you are having daily to daily snapshots, so not much files you are updating, or in that case, you can increase the scanner threads and also copy threads. So it's very easy to tune now. Okay, so I want to go a bit low level here, a bit code level, might be a bit boring, but yeah, file mirroring is easy. So we have task, file task, one queue, and we will throw our file copying task to that queue, and all the threads are just pull out and copy those files. But there are some little tiny details. One is for smaller files, we know that those are the problems for Cephfs-mirror. For smaller files, we try to batch those smaller files, make it maybe read first a 4 MB chunk, buffer it, and then writing it, the smaller files at once. So yeah. So for user, knobs are maximum file in flights and number of copy threads. And next one is tricky. That was directory sync pool. So basically, we want to have the metadata IO as also parallelly or concurrently. But problem is the directory tree has a dependency, right? So parent has to be created before child's subdirectories. So how we handle that? So let's say we task this way. So it's kind of we are scanning the whole tree with breadth for search, but it's in a bit different way. So you will have, let's say, task, sync tree task. So my task is to create the directory and splitting those subtasks and sending those subtasks to the queue again. But the problem is you cannot use, your queue is limited. So you cannot just throw all the tasks to the queue. So how it happens? So if now the problem is if we limit the queue, then there's a chance we will fall into a deadlock. But how we'll resolve it? Okay, the resolve is, okay, so I have a task and my task is to do the task and submit those subtasks into the queue. So what I will do, instead of when I find that is my queue is full, instead of pushing into the queue or waiting for the queue has some space, I will just do it myself. So yeah, and also there is a delete tree task. As I said, ordering and dependencies part. So the second part, but the bounded frontier and BFS, DFS as a solution. So we, as I said, we are enqueuing child sync tree task. So when queue has headroom, but what if queue doesn't has headroom? So at that time, should I maintain that wait notify pattern? I don't think so, because it can fall into a deadlock. So instead of pushing that task into the queue, I will just do it myself. So DFS and opportunistically always enqueue when slots are free. So that actually keeps memory predictable and spread work across threads. I think we are on the last stage. So the concurrency part here already, there are some variables with that global variables, we can tune that, like Cephfs-mirror rescanning thread, that's the number of threads in the metadata pool, and file sync thread, which is for file copy workers, and yeah, pool queue size and file pool queue size is pretty common. And another thing, sync latest snapshot. That means, for example, if you take snap 1, snap 2, snap 3, snap 4, you can just skip snap 2, snap 3. You can just say, if you make it true, then it will just sync skipping snap 2, snap 3, just sync the latest snapshot. So you will always get the latest snapshot in sync. And remote div base upon start, that is basically forcing, there are a lot of, I would say, bugs in libcffs. So forcing for the remote div base as the base to find the difference between the two file systems. Yeah, so also we did some, it's pretty small. So we try to, this is currently not in current Cephfs-mirror, but in our patch we have it. So basically, while mirroring, you can track how many files are synced, how many files are deleted, how many directories scanned, a lot of information while going on. Yeah, so that's kind of it, but I didn't go through the comparison with the current approach and the approach I used, because current approach is very slow to finish, even for, this is just I try to sync the Ceph directory, Ceph repository, and Linux repository. This took almost, the Ceph repository almost took, and it's just a dev cluster, so it took almost 30 seconds, and that one took 20 seconds sometimes, but current Cephfs-mirror will take maybe 30 minutes. It's very slow. Yeah, and we have some customers. One customer, could take some actual data for real comparison, but the problem was they had to restructure their cluster. But last time we had information that is they are kind of having bandwidth utilization from 40% to 90%. So it's with proper tuning, we can obviously do that. And also, Cephfs-mirror is a daemon, so you can spawn multiple daemons, and yeah, through that, obviously, you can get more throughput. Thank you. And any questions?
So, thank you very much. Are there questions regarding the speech?
Is there a PR for that?
Yeah, there is a PR. Yeah.
All right. So, thank you very much. All right. So, thank you very much. Mahamudur Rahaman Sajib, it was a pleasure to have you.